Okay, so welcome back to another video. So here we have a little geometry problem, and that is constructed is that we have a quarter circle, and inside this quarter circle inscribed is we actually have a equilateral triangle that you see with these side lengths with these double hashes, so the sides are congruent. So we actually want to find what the blue area, so in other words, what the area of this equilateral triangle inscribed is, if we have that the radius is equal to 4. And we also have a right angle over here where the quarter circle is inscribed over here as well. So it's pretty straightforward to know that equilateral triangles is that we know that the formula is described as follows. So we have the area of, abbreviate this as EQ and then a triangle symbol. We know that that's actually going to equal the square root of 3 divided by 4 multiplied by a squared, where a is actually the side length of your equilateral triangle. So using this formula, it's actually, we're gonna have to create a little bit of some, add a little more into the construction to actually help determine what that side lengths of each of those, of our equilateral triangle is. And then we can actually just move forward from here. Pretty simple. It's pretty much just gonna be a short video today, but I haven't really covered much of geometry problems in a while, so I thought we'd do something a little bit more, simple and nothing too overwhelming in other words. So let's actually just jump right in. Let's actually create this little angle bisector. And so when I draw from the length from this point to here, this will actually create half the length of this entire, side over here. So right here, I'll just draw the dotted lines representing, the bisection. With this, we can actually say that because, all the sides are congruent and it's split in half. So I'll actually call this side length A and then A over here. And so this is also to imply that the entire side length of our equilateral triangle is going to be double that. So this is actually going to be called 2A and 2A over here. Using our formula for the equilateral triangle, so if I were to just plug this in, so we have the square root of 3 divided by 4 multiplied by 2A squared. So that would have to mean we have 4A squared, but then the 4's will cancel. And so we have that our area of this equilateral triangle supposedly is supposed to be the square root of 3. Right? Okay. But also we have this bisection that, there's a 90-degree angle at the base right here. And so with these congruent sides, so we actually form ourselves a little 45, 45, 90. So that's also implies that everything here with this bisection here from this length to this length here, or this point to this point, that this actually has to equal the length of A as well. Where does this really take forward? Because we actually need to know, we know what the our side length is to construct this area of this triangle, but we really don't know exactly what the height of this. And this is extremely important because we actually want to know what the length of A is, and so we need to figure out the length from this height of this equilateral triangle is. But it's important that we also gave that R is equal to 4, the radius. So by doing so, if we know that for example, we use our standard base times height formulas divided by 2 for a triangle in general. And if we set this just equal to A squared square root of 3, pretty self-explanatory to say that if I were to plug the base length, which is 2A, and then times H, so the A's will cancel, or the 2's will cancel, and so we're left with A times H is equal to A squared divided times the square root of 3 divided A. And so we see that our height is going to be equal to A times the square root of 3, implying that now we actually have a sum of lengths that's going to equal our radius length. So then R is going to equal A, then add this with A square root of 3, which is equal to 4. And then simply we can actually solve for our length of A, which simply enough, we can actually just do a little bit of algebra, factor out the A. So we have that A is 1 plus the square root of 3 is equal to 4. And so we see that A indeed is just equal to 4 divided by 1 plus the square root of 3. Smooth sailing from here. All we do is just plug this A back into our equilateral triangle formula over here. So now we have 4 divided by 1 plus square root of 3 squared multiplied by the square root of 3. And so now simply we have 16 divided by, so 1 plus, or this is actually just, 1 plus square root of 3, then the quantity square. We see that this is 1, add this with, so it'll be 2 times the square root of 3, and then add this with 3, so, because the square roots cancel, so we have 4 plus 2 times the square root of 3, and then we'll multiply the square root of 3 on the top. Now we can actually continue simplifying this a little further. We can actually divide a 2 from both the numerator and denominator. They get rid of each other out. So by doing so, we have 8 multiplied by square root of 3, all this divided by 2 plus square root of 3. And then if you do the a little bit more simplification, we can actually do the conjugate. So 2 minus square root of 3, then 2 minus square root of 3. We see the multiplication over here is that this is 2, let's see, it's 4, and then minus 3, square roots cancel, so it's just 1 on the denominator, so that's great. And so really we just have to, just do a little bit of distribution over here and say that the final answer of this blue area of our, triangle is going to be equal to 16 times the square root of 3, then 8 times square root of 3 times square root of 3, so that's 8 times 3, so subtract 24. And so just like that, we have found our area of this, the blue area, aka this equilateral triangle inscribed of our, quarter circle. So simple enough, right? So yeah, that's pretty cool if you ask me.